us during this time, and hope everybody's safe, and hope everybody's learning how to wash their hands. Carrie, thank you for donating your time, and I think a lot of the folks will get a lot out of this. And Terry's with GE Multilin, which is now called GE Renewable Energy, I believe, and I'm going to let Terry take it away.
Okay, just as a matter of logistics, when someone wants to ask a question, should they use their voice or should they use the chat?
They can go either way. We like both.
Okay. Okay.
Sometimes
We
it's
can go
too
either
much
way.
words to put in a chat.
That's right. Okay, we can go either way. So symmetrical components. This is a topic that we could spend hours and hours on, or we could spend a lunch and learn on. I'm going to try to do this in a lunch and learn in this hour. What's probably going to happen is I'm going to hit right at the hour. So I can go over the hour, 15, 30 minutes, whatever you guys want to address questions that we have, or if we get questions along during the WebEx, then I may run into that past the hour. But pretty much what I'm going to try to limit my discussion to is you can't really talk about symmetrical components without first talking about phasors, how we add phasors, what phasors are, and what they mean. And then basically I'm going to review what symmetrical components are. And to me, the real benefit of understanding symmetrical components is in identifying fault currents and calculating some of those fault currents. Now, we won't have time to calculate some of the fault currents, but what we will be able to do is we'll be able to talk about how these sequence networks interact to produce fault currents. And then as a means of having sort of a conclusion, I'll give you a quiz, right? We'll have a quiz that will help us sort of solidify some of the concepts that I mentioned. Don't worry, you won't be graded, okay? So with that said, let's talk about what a phasor is and how we review it. Now, when I set an overcurrent relay, right? When I set a overcurrent element in a microprocessor-based relay, usually I set a pickup value. And that pickup value in our relays, it's in per unit. And that's in per unit of CT. So I'm really translating this into some quantity. So if it's a 2005 CT, and I set that at 1, that means it's picking up at 2,000 amps, right? But what really is 2,000 amps? Well, I kind of think of that as the RMS quantity, but it could be the phasor quantity. And what a phasor is it is merely a mathematical technique to turn this sinusoidal waveform that you see. Let's turn my pen on. It's a mathematical technique to turn this sinusoidal waveform into a magnitude and angle, right? So, what we produce on the back of the relay, or what we wire to the back of a relay, is that sinusoidal waveform. And my mind can't add 2 sinusoidal waveforms. Some of you guys say you can do that. I want to see you do that when they're offset by 30 degrees. It's easy to do if they're offset by 180 degrees, but when they're 30 degrees, my mind can't really add 2 sinusoidal waveforms. Now, what I can sort of do better is when I turn this into a magnitude and an angle. And so that's what the relay does, is it uses mathematical techniques, typically a Fourier transform, to turn that sine wave. It's going to sample that sine wave and then turn that into a magnitude and an angle. Then it can apply that magnitude to comparators, like the comparator for the pickup of that time overcurrent element that I described. And so doing that, we can operate. Now, in our discussion of symmetrical components, it's also necessary to understand how we add and multiply phasors. So when we add phasors, Basically, what I would do if I'm adding A1 and A2 here is I'm going to take A2 right here, and if I want to do this graphically, I could just superimpose A2 onto the end of A1, and the resulting vector would be my sum of those two, which here it's this vector here at this angle, right? So it's a magnitude and an angle, that's why it's a vector. Now, that's how I add vectors, or how I add phasors. If I need to multiply phasors, and it will be important to be able to multiply phasors for symmetrical components because of something called the small a, or the A factor. If I'm going to multiply those, what I'm really going to do is I'm going to add the angles. I'm going to sum the two angles. So if angle 1 here is positive 30 degrees, and angle 2 here is minus 60 degrees, my resultant here, my resultant waveform here ought to be at minus 30 degrees, because the sum of minus 30 and the sum of minus 60 and a plus 30, that's going to be minus 30 degrees. The main thing to remember is when I multiply two phasors, I'm going to multiply the magnitudes. But more importantly, for our discussion of symmetrical components, I'm going to add the two angles together to get the resultant angle. Okay. So with that said, let's talk about symmetrical components. We've done enough of an introduction. Let's get into the meat here. So we can have a symmetrical or a non-symmetrical system. Now, if I look at this system here, this is a balanced three-phase system. It's perfectly balanced. If those waveforms there, if they represent my voltage that I'm applying to a balanced three-phase system, then I can easily calculate my phase currents, right? I can calculate my phase currents because if I know my impedance, I can just use Ohm's law. If I put a 3 ohm impedance that's balanced across this balanced voltage, I've got 1 unit of current. And that 1 unit of current, if it's a purely resistive impedance that I put there, they'll be at 120 degrees to each other at a unity power factor. You know, if there's some impedance, there'll be some, if there's some reactive impedance, there'll be a shift there. But this sort of system is real easy to analyze. The problem is that during fault conditions, we don't always have this system. And in fact, if I can have systems that are unbalanced for other reasons, right? I can have unbalances from, my voltage could be unbalanced because of system faults out on my power system, faults into my power system. If my power system happens to be a distribution utility, you know, medium voltage distribution utility, and I have radial single phase taps, then I'm going to have unbalanced loads. So my system might look like this. So if I took that system and applied it to my currents, or I applied that system that I show here, this non-symmetrical system, if I applied that to my system, if this is the voltages, calculation of the currents is going to be much more complicated. And in fact, I'm going to have some currents that are probably going to be flowing into the neutral. So I have neutral currents that I've introduced there because these three quantities here don't vectorially sum to 0. So previously, when I say previously, before someone invented symmetrical components, there wasn't a way to analyze this system, this non-symmetrical system that I show on the right here. There's no way to do this. So Charles Prometheus Steinmetz, he came along in 1913 and he developed a mathematical technique that would let us analyze that system. And what I find fascinating about this is that this occurred in 1913. Not that it was so long ago, it was that it was so recent. By 1913, the current wars were over. We were already deciding that we were going to distribute and generate and transmit electrical energy via AC three-phase power systems. And so there was a long time that that those guys didn't have the ability to calculate what would happen if they had a ground fault, or what the currents they could expect to see if they had a ground fault. They didn't have that capability, and it sort of boggles my mind to think that they were transmitting, generating, and distributing electrical energy, and they didn't have those capabilities. So that sort of boggles my mind. But when he developed these mathematical techniques, what that did for us as a species and us as an industry was it'll let us analyze those systems, let us calculate those systems, and it unlocked a whole new way for us to do protection and for those transmission, generation, and distribution systems. So let's talk about his mathematical technique. So if we really look at his mathematical technique, what it actually says is we can take a unbalanced in-phase system and turn that into n different systems of balanced conditions. So for our three-phase power system, what that means is if I have a unbalanced three-phase power system, I can turn that into 3 separate balanced systems because it's a three-phase system. And so the way that we describe this inside of our world is we describe this as a positive sequence network, a zero sequence network, and a negative sequence network. Now, the positive sequence network is what we expect to see in place if we have balanced power conditions or balanced load conditions or a balanced power system. And this particular network, it looks just like what we expect to see on our phases in the steady state. So we've got a ABC rotation going counterclockwise. So that means if I were to imagine this set of vectors turning in this direction, that the phases that would cross, the sequence of phases as they crossed the zero axis would be A, B, and C. So that means the ABC phase sequence. All the phasors are of equal magnitude and equal angles from each other. Now, that is the positive sequence network. Negative sequence network is, there's no sequence to it. All the phases are equal magnitude and all the phases are in phase with each other. And then the negative sequence network here, it has a reverse phase rotation. So for it, what I expect to see is if my eyeball's standing right here, so this is my eye. Let's see how good of a drawer I am. Oh, I've got eyelashes at the top, not at the bottom. I guess I do have them at the bottom too. But if my eye's standing right there looking and this thing is rotating counterclockwise, I expect the sequence to pass my eyeball to be ACB. So it has ACB rotation. But again, all of the phases are equal and all of the phases are equally spaced by 120 degrees. So that's what these 3 symmetrical components networks become. So how the next question we should ask ourselves is, well, how do I take my measured quantities that I see on the relay and turn those into these symmetrical components so that I can do calculations on fault current, load current, those sort of things. Well, that's what we get to in 2 slides, okay? But right now, the first thing that we need to talk about is this A operator.
Hey,
And the
Terry,
A operator,
a question came in. Why isn't, I get this argument with customers, why isn't the rotation clockwise?
why isn't the rotation clockwise?
We always go counterclockwise.
Someone probably at some point chose counterclockwise, and they chose to say A, B, and C. So if you chose to do this differently, you just have to you would have to choose to show everything differently. So a decision was made in the way that we show things way back in the day, right? Does that make sense? Okay. Okay. So to understand this mathematical technique, one of the things that we need to understand is the A operator, because the A operator is used in the mathematical techniques that Steinmetz developed. Oh, I'm sorry, not Steinmetz, Fortichet. Fortichet developed these in 1913. Steinmetz developed phasers. But this operator is used, and basically what the operator is A rotates by 120 degrees, and A squared rotates by 240. So if we were to look at this, what A equals, so A equals 1 per unit at 120, right? And then A squared equals 1 at 240, right? So basically, we're going to take our quantities and we're going to multiply them by either A or A squared. And what that's going to do for us is that's going to shift the angles of those quantities, since we're multiplying by 1 per unit. It's going to shift it by either 120 degrees here or 240 degrees. All right, so let's look at what the A, how we use the A operators. So the equation for the positive sequence component, this could be the positive sequence current, positive sequence voltage, whatever, is we're going to take A phase, we're going to shift B phase by 120 degrees, and we're going to shift C phase by 240 degrees. And we're going to take 1/3 of that quantity. So if this is my balanced three-phase system, A, B, and C, and I'm going to shift B, let's see, so I'm going to shift B by 120 degrees. So that puts B right here. And I'm going to shift C by 240 degrees. So I'm going to shift him sitting right over here. That puts B and C phase in phase with A. And I sum those together. If they are 1 per unit, that sum is 3 per unit, which is why we have the 1/3 here. So if we have a completely balanced three-phase system, we expect the positive sequence component to be equal to the magnitude to be equal to the phases, to any one of the phases. And they have to be the same because I just said that they were all, that it was, a fully balanced system. Negative sequence, we're going to take the same thing almost, but we're going to swap the A2 and the A here, right? So that means, let me get my eraser out here. Oh, actually it's wrong here. So that means I'm going to have A here. I'm not going to do anything with A. I'm going to take C and I'm going to shift it by, C by 120 degrees, which puts C right here, right? And I'm going to shift B, where's B? By 240. So let's see, we're going to go, that's going to put B right here. Now, if I take this C and I superimpose it on A, right? And I superimpose B on that. That means my negative sequence components are going to be 0 if I have a truly symmetrical power system, right? So let's get my eraser out here, and let's talk about the 0 sequence components. So 0 sequence components, I'm going to take my vector sum of my 3 phases, basically, and it's 1/3 of that. So oftentimes what you'll hear me say is that neutral current equals 3I0, right? So I often say that, and that's because neutral current is basically the vector sum of the 3 phases right here. So neutral current is the vector sum of the 3 phases, and 0 sequence current is 1/3 of that. And so if we imagine this balanced 3-phase system that I show right up here, right? If I take C and I put it on the end of A here, and I take B and I put it on the end of that vector, I come back to 0. So I don't have any, in a balanced 3-phase system, I don't have any 0 sequence components, right? Now, once I've calculated and what we'll do is we'll calculate sort of these sequence components, but at some point we probably need to turn them back to phase quantities, right? So we know what the current is on A phase or B phase or whatever. And we can use these equations here on the lower part, to take those back to actual phase quantities. So if I know my positive, negative, and 0 sequence quantities, if I know my positive, negative, and 0 sequence quantities, I can calculate my phase quantities as well. So remember that balanced 3-phase system that I spoke about earlier, and I went through all these other scenarios on. In a balanced 3-phase system, I have positive sequence quantities, but no negative sequence quantities and no 0 sequence quantities. So if I put plug those quantities in and get IA, IB, and IC, they're all going to be equal to that positive sequence quantity, because I2 is 0, I0 is 0, so we only have I1 here. These two are 0 here, so we've only got I2, and it's shifted by 240 degrees, which would put it at minus 120, which is where we expect B to be. And these guys are 0, and IC is shifted by 120 degrees, which puts it at minus 240, which is where we expect it to be right here. Okay. So let's look at this a little bit more in detail on a actual system, right? So there's a fade here, and I don't particularly like that fade, but let's look at this system here, and let's look at my quantities here. So here's my VA. Let's just look at my voltages. So if I take my voltages, and I'm going to shift B by 120 degrees, so that puts it in phase with A, and I'm going to shift C by 240 degrees, A2, that puts it in phase with A. So if it's balanced like this, that vector sum is 3V1, or if it's actually 3V1, but V1 is 1/3 of that, right? So since this is a balanced system, if I look at my negative and 0, I sort of expect those to be 0 also, but let's take a look at it. So here's my A phase. A phase is sitting at 0 at 120, right? So I'm going to take B for my negative, and I'm going to shift it up to where C was. So it gets shifted. Actually, it gets shifted by 120. So it gets shifted up here, and then C gets shifted down to here. So what that sort of looks like is that looks like the vector sum of those, as long as it's a balanced system. Here's V2 that shifted B, right here. And then here's that shifted C right here, and those vectorially sum to 0. And my zero sequence quantities in this system, I'm just going to take the vector sum, right? So if I take VA, superimpose C onto him, just like I did a few minutes ago, and B onto that gives me 0. Okay. Now, where this becomes more interested in is in these scenarios where I have an unbalanced system. So if I look at this scenario that I show with my currents below, if you look at my B phase current, it doesn't look like it's got a smaller, the angle looks about right compared to A and B and A and C, but the magnitude is significantly less than B and C. So let's look at what that would do, right? If we had this situation where we had same phase displacement, but a smaller magnitude on B. Now, this is something that could actually happen in the power system, right? If I had more resistive impedance, just strictly resistive impedance on B phase than I did on A and C, I could see this. I could see this because I've got more impedance, so that means I've got less current. So let's take a look at what this does. Does this create positive sequence quantities? Yes, it creates positive sequence quantities if I shift B here to be in phase with A and C to be in phase with A. Yep, I've got positive sequence quantities. They're going to be, the positive sequence quantities are going to be a little bit less A or C phase, right? Because it's 1/3 of this quantity. Okay, now do I have negative sequence quantities? Well, if I take my A phase here, and then I take my shifted C and put it here, right? And then my shifted B and put it here. Well, now, yes, there is a small amount of negative sequence current right there. So negative sequence current would actually be 1/3 of that. So there is some negative sequence current. The other question is there zero sequence current? And yes, there is. And if I take A here, take A, don't do anything to it, take and shift C, or I'm not shifting at 0, I'm just going to superimpose C on the end of that. And then I'm going to impose B on the end of that vector. Then here is my 3I0. So once I take 1/3 of that, I do have some small quantities of zero sequence current. Now, I mentioned that what this sort of looks like is maybe I've got an unequal impedance on the 3 phases. What this might also look like is if this is a distribution system, medium voltage, utility distribution system, and they've got a lot of radial taps, and they don't have their system balanced particularly well, then they might have this sort of scenario where they've got some zero sequence current that is just from this unbalanced load. All right. So let's look at what some of this means on some different conditions. So the condition that I'm showing right now is an inverted phase. And there is one power system phenomenon that will create an inverted phase. It is a wiring error. So the only way that I can have an inverted phase like this is if I have a wiring error. So if I look at B phase here, B phase is sitting, it should be sitting down at -120, and it's really sitting at about 60 degrees. So that's not right. So what happens if I have this sort of condition? Well, if I look at A phase here, and I take this B here, and I superimpose it on the end, that gives me this point. And then I take C and superimpose it on the end of that one to here. That gives me a zero sequence quantity, right? So my zero sequence quantity is 2/3. And let's look at negative sequence, right? So if I take my A here and I'm going to shift my B by 240 degrees, so that moves him down to here. And then I'm going to take C and I'm going to shift it by 120 degrees, which puts him here. That gives me this negative sequence quantity. And then if I take I1 here, now I'm just going to, on I1, here's my A phase, right? B phase is going to be shifted by 120 degrees, which puts it right here. So those two sum to 0. And so C phase then shifts by 240, which puts it right there. So he's sitting right here. And so what that means is by when I take 1/3 of that sum, of that vector sum, my positive sequence quantity is 1/3 per unit at 0 degrees. So anytime, and the reason I say this, and we'll talk about this in a few moments, we talk about the way the fault sequence networks interact, is it is really impossible for my negative and 0 sequence quantities to be greater than my positive sequence quantities. And if I see my negative and 0 sequence quantities larger than my positive sequence quantities, that is a wiring error. So one of the things that we always should do as we commission protective relays or meters is we ought to look at the quantities of positive, negative, and 0 sequence components from our metered quantities to see that we have eliminated any wiring errors that we expect. This can immediately point out, hey, I've got a wiring error, or it may immediately point out, it probably immediately points out you've got a wiring error, but then you got to figure out what that wiring error is. You know, another wiring error that you could have is if you have B and C phase rolled, right? So if I've got B and C phase rolled, I calculate my quantities. Look what I've got here. I've got A phase sitting right here. B phase, I superimpose it on the end, and I'm sorry, C phase, and then B phase there. So I've got 0 sequence components and 0 sequence current. Now, that's great, that's good, right? But look at what my positive sequence is. Well, I've got IA sitting here, right? And then I'm going to take B and I'm going to shift it by 120 degrees, right? So if I shift it by 120 degrees, that puts him right here. I'm sorry. This is positive sequence. I'm going to shift it by 120 degrees, which would put it right here. So here's my B phase shifted. And then I'm going to take C phase and I'm going to shift it by 240 degrees, which you put it where B was. So here's my shifted C phase. What I've got there is I've got 0 positive sequence quantities. Now, that doesn't make sense to me. That's starting to not to make sense. And then when I do this same scenario with my negative sequence quantities, here's my IA. So IA sitting right there. I'm going to shift B by 240, right, which you put it all the way around to here, in phase with IA. And then I'm going to shift C by 120, and that puts it in phase. So these vectorially sum to 3 per unit. When I take 1/3 of that to calculate my I2, it's 1 per unit. So in this case, I've got 1 per unit of negative sequence current and no positive sequence and no 0 sequence. I just said that positive sequence quantities can't be less than negative or 0. And in this case, we've got negative sequence quantities that are greater than positive sequence quantities. That's a wiring error, right? Okay. So a summary of symmetrical components is, hey, this is a way to take an unbalanced system, turn it into a three balanced systems. With those 3 balanced systems, we can then start analyzing our networks. We can then start analyzing fault conditions. So let's see what that looks like if we're going to start analyzing fault conditions, right? Because the only reason we're really talking about this mathematical technique is so that we can analyze fault conditions, that we can look at fault currents and ascertain what kind of fault that was. Or we can do calculations on fault current and or calculate fault current or calculate quantities to determine what our fault current is. So let's look at an example system. So in sort of this scenario, this is our example system. So I've got a relay and this is a metering point. So this is always important to show where I'm metering at, right? And I'm metering current quantities there. I didn't show it, but I probably also meter in voltage. Well, pretend that's a VT. Pretend that's a VT that I just drew. But I'm probably also measuring voltage quantities there. Now, I've got some sort of source behind me. I've got some sort of load in front of me. I've got some sort of source or system impedance behind me. And I've got a line impedance out to my load. And all of those things matter. Now, what I get out of these sequence networks is I get the ability to build 3 different sequence networks. So I can have a positive sequence network, I can have a negative sequence network, and I can have a 0 sequence network, right? And we'll talk about why in a few minutes, but what I show on the screen right over here, is how these 3 networks or how these sequence networks interact for a phased ground fault. So one of the key things that we'll have to know and we'll have to sort of realize is how these 3 separate networks connect and interact for different faults and different fault types. Now this is a phased ground fault. Now there's a few things to take in, and the things to take in that are really important is these questions that I'm asking. You know, if we look at that network there, what I can really see here is, you know, where I draw this little line here and here, this is where that relay is sitting at, right? So this is where my relay is sitting at, or my metering point is. So if my metering point's right there, this V2 that I show here is the negative sequence voltage that relay can calculate, the positive sequence voltage that relay can calculate, and the 0 sequence voltage that relay can calculate. There's also a negative sequence current, right? A positive sequence current and 0 sequence current. And what's fascinating about this is, where is the voltage the largest? Well, the voltage is the largest in my positive sequence network right here, right across the voltage source. That's where my voltage is largest in the positive sequence network. Now, my fault location is actually where these networks connect, right? So as I look at this, my negative sequence voltage is greatest right here, right? Because the further, you know, as I get closer to the fault, the more negative sequence impedance I have here, the voltage that I see right here, at the fault location is going to be equal to the negative sequence current times this negative sequence impedance here. So as I move closer to the fault, my negative sequence voltage gets higher. But if I look at this, as I move closer to the fault, my positive sequence voltage gets smaller. Likewise, you know, my 0 sequence quantities, if I look at them down here, that 0 sequence voltage that's sitting at the fault location, it's dictated by the 0 sequence voltage, the 0 sequence impedance sitting right here, and the 0 sequence current that's been driven through that impedance. So as I get closer to it electrically, as I get closer to the fault location, my zero sequence voltage goes up. The only thing that I'm able to measure for zero sequence and negative sequence voltage at the meter location is this system impedance, zero and negative sequence impedance. So basically, the voltage that I measure at the meter location is for negative sequence and zero sequence is actually going to be that negative sequence and zero sequence current being driven through those respective impedances. So if this quantity is a lot bigger than this quantity, right, I may not have much negative sequence voltage or zero sequence voltage at the metering location. That's one of the things to take into account. The other thing to take into account is I have a source in my positive sequence network, right? Where's my source for my negative sequence network? Where's my source for my zero sequence network? Right? That's a real good question. And in reality, the source for negative and zero sequence quantities is the fault itself. And that's what generates those quantities. There isn't a source in the negative sequence and the zero sequence networks, only in the positive sequence. So it is that unbalanced load or that fault that generates negative sequence and zero sequence quantities, right? All right. So let's talk about different fault types. I said that network that I showed a few minutes ago was for a phased ground fault. So let's talk about how I know that or how I derive that. Now, in reality, I got that out of the book, but we can derive it, right? So what we know about a phased ground fault is that the faulted phase is very large, right? So the current, for example, I'm talking about current, right? The fault current on the faulted phase is very large. The unfaulted phase are small or almost zero, especially compared to the faulted phase. Somebody's got some background stuff going on that's driving me nuts.
Somebody has called in on their telephone. You need to mute your telephone. I can mute people on the web. I cannot mute people on the telephone.
Yeah.
Please
Whoever's on the telephone, man, I can tell you this is a lunch and learn because I can hear you slopping. I can hear you chewing. If it was any other noise other than chewing, I'd be fine. Okay. So on a phased ground fault, we know that the faulted phase is very large. The unfaulted phases are almost zero, right? So, and my apologies to everybody because now everybody knows that that was chewing and that's going to drive them insane too. So what that looks like in the real world is, so if A phase is faulted, it's some value, some big value. B and C phase, right? B and C phase, B and C phase are, we're going to call them zero. They're probably pretty small, but they're going to be small enough we're going to call them zero. So if we calculate the zero sequence quantities, let's just sum those three dudes together, and that's going to be X, right? So we calculate positive sequence, negative sequence quantities. Well, IB and IC are zero, so that means we're equal to IA, which means that I0 equals I2, which equals I0. So I2, I1, and I0, the sequence networks are all equal magnitude, and they're all in phase with each other. That means that the only way that I can create that sort of network is if my three networks, my positive, my negative, and my zero sequence networks, are in series with one another. So this means that the networks are in series and they're on a solidly grounded system. Now, if there was a ground impedance in here, I could expect some smaller quantities, but I'd still expect those quantities, positive, negative, and zero sequence, to be similar. So when I look at a fault current, right? When any of us look at fault currents from an oscillography record, you know, one of the things that we probably first right off the bat do is if we see a phase current really, really high, if we see it really high, but we see B phase and C phase really low, we immediately say, hey, that is an A phased ground fault. We know that because we know that A phase current's got to go somewhere and is not going on B and C phase or we'd see it. But in reality, what we're really doing is we're calculating zero sequence current in our head. We know that zero sequence current's got to be going somewhere. It's going through the neutral to the ground. And so we know that this is what our network has to look like because positive, negative, and zero sequence quantities are the same, right? So that's what the sequence networks look like on a solidly grounded system with a PhasetoGround fault. Now, what happens if we have a phase-to-phase fault? What do we know about the fault current there? Well, there we know that the faulted phases are very large and that the unfaulted phase is small and almost zero, right? So if we have phase-to-phase fault, what does that look like? Well, let's say IA is the unfaulted phase, so his current zero. That means that the current in B has got to be coming back on C, right? Because there's no other path for it to get back to its source. It's got to have a complete circuit. So that means IB equals minus IC. And those are both equal in magnitude to X. I should have drawn absolute values around that. IA, so if we calculate zero sequence quantities, IA plus IB plus IC, I got zero because A is zero, B is X, and C is minus X. That sums to zero. If I calculate positive sequence quantities are going to come out to be equal to the square root of 3 of X, and negative sequence is going to be the same thing. And positive sequence, so basically positive sequence equals negative sequence, and zero sequence is not involved. So knowing what those three networks look like, I should be able to interconnect those three networks in a way that produces these currents. So if I look at what that looks like this, right? So my zero sequence network is not involved. So it's sitting down there, hanging out down there by itself. Since there's not a source in that zero sequence network, there's not any zero sequence current flowing, which is what we calculated from the previous slide. Likewise, we do have negative sequence current flowing because the positive sequence network and the negative sequence network are connected in series. And so we do have negative sequence current flowing, and it's equal to the positive sequence current, right? So negative sequence current equal to the positive sequence current, and they're flowing in the reverse direction to each other, basically. So that's why we see that I1 equals I2. So this is what the networks look like for a phase-to-phase fault. So when I see negative sequence current equal to positive sequence current, no zero sequence current involved, that immediately makes me think of a phase-to-phase fault. Okay, now what happens on a phase-to-phase fault? Well, on a phase-to-phase fault, all the phases are very large. Unfaulted phase is, what happens on a phase-to-phase to ground fault, right? On a phase-to-phase to ground fault, all the phases that are involved are large. The unfaulted phase is small, almost zero. The faulted phase voltages are also zero, or almost zero. So the faulted phase voltages collapse. We got to get voltage involved in this particular example because we can't derive this particular sequence network without the voltage. So let's look at what we get there. So IA equals 0, VB equals VC equals 0. It's a B to C phase fault, so all the current going out B phase has to come back on C, and that's equal to a magnitude of X. We vectorially sum those. And what we get is we get 0, right? We look at negative sequence current, negative sequence voltage, right? I mean, positive sequence current, positive sequence voltage, they're the same they were in the last example. Main thing is that they are equal. Okay, so for a phase to phase to ground fault, this slide is wrong. I'm sorry, guys. This is the first. This presentation had modifications made to it, and I didn't check the math. But for a oh, this slide isn't wrong. Never mind. I'm wrong. It happens. Okay. So negative and negative sequence current and voltage are shown here, right? I0 is 0. So if we show these sort of networks, what this sort of looks like, the only way we can get positive sequence voltage to be equal to negative sequence voltage equal to 0 sequence voltage is to connect the 3 networks in series. All right, not series, but in parallel. The 3 networks in parallel and the 3 currents summing to 0 also means that they have to be connected in parallel. So that's what the 3 networks in parallel look like, are the phase-to-phase ground fault. For a 3-phase fault, we know that all of our currents are very large and equal if it's a balanced 3-phase fault. So IB equals IC equals X. So that means I0 is going to be 0. I1 is X. I2 is 0 because it's a balanced fault. So I1 equals I2 equals 0. These 0 sequence and the negative sequence currents aren't involved. So that means those networks aren't connected. So for a balanced 3-phase fault, we only have positive sequence currents flowing. And the positive sequence network is the only one involved. This is also what we expect for normal load conditions, balanced load conditions. Okay. Now this becomes a little bit more complex because transformers do things to our sequence networks. So if we look at our positive and negative sequence networks, right? We look at our positive and negative sequence networks, it doesn't matter on the transformer type of connection. We always pass positive and negative sequence quantities. But depending on the transformer connection, right, will depend on whether or not we're able to see or pass negative or 0 sequence quantities. It will also depend on whether or not the transformer is grounded in some way. Basically, it depends on whether or not we have a ground source. The transformer, if it's grounded, can be a ground source. If it's a ground source, then we can pass 0 sequence current. If it's not a ground source, we can't. So let's talk about this particular transformer. Now, one of the things I haven't mentioned so far is what do these quantities typically look like? Well, if this is the transmission system here, positive sequence, negative sequence quantities are almost the same. 0 sequence quantities can be a little bit different. Part of the reason that they're a little bit different is because there may be other transformers upstream that block 0 sequence quantities. There may be some ground resistance. There's some things that can affect the ground impedance, right? For the transformer itself, again, negative sequence, positive sequence impedances of the transformer, almost identical. The same is true of the line. The places where negative sequence and positive sequence impedances become different are in things like motors. Negative sequence impedance of a motor is very different from a positive sequence impedance of a motor. That's a topic for another time. But for the power system itself, the lines, the conductors, typically the impedance itself for positive sequence and negative sequence will be very similar. Zero sequence can be a little bit different because of the things that I'm going to talk about in the next slide. If we look at this scenario here, and we look at what transformer that looks like to us. So very important is, where's the meter location? So that's the CT that I can calculate zero sequence quantities from, and that's where I want to do that. It looks like this side of the transformer is grounded, right? So my metering location is going to be right here and right here, right? Let's look at what that looks like when I interconnect the two power systems, right? So since that transformer has a ground source, it can provide ground fault current, which means it can provide, since it's got the center, the Y point grounded, it can be a ground source. So it can be a ground source. If my metering location, I've lost my cursor, there it is. My metering location is right here and here and here. At that relay, I can calculate zero sequence current, negative sequence current, positive sequence current. At that meter location for ground fault downstream of that device, those negative, positive, and zero sequence quantities should be the same magnitude. My negative sequence voltage is going to be a little bit different. My zero sequence is similar. Now, what's important to note is if my meter location was on that delta connected winding, so if my meter location is right here, I have a different scenario. My meter location is right there. That means my meter location is here, here, and here. Now, I can still provide zero sequence quantities to that fault on that distribution system, right? But what I can't do, and I can see the negative sequence component of that fault, and I can see the positive sequence component of that fault on the H side of that transformer where I drew my X. But what I can't see is those zero sequence components, which are sitting, right there. And the reason I can't see them is because that transformer blocks that, right? So, as a means of concluding, let's take a little quiz, right? So I'll give everybody time to think about this. So here's the problem. Problem number one, I have positive and negative sequence currents. The positive and negative sequence currents are equal and opposite. Zero sequence current is a different value than the positive and the negative sequence. Positive, negative, zero sequence voltages are equal. So the question then becomes, well, which one of these things looks like that? Now, what this diagram here, you can find diagrams like this in a lot of different textbooks. And these diagrams represent the different ways for different fault types that the sequence networks are connected. So right up here in the top is the fault type, and then this represents the positive and the negative and the zero sequence impedance. So, if I want to identify this, what I need to do is which one of those conditions that I just showed causes positive and negative sequence current that are equal and opposite. Means those two are in series, and positive, negative, and zero sequence voltages are equal, right? So let's take a look at this. Well, this one's out because they aren't in series. Can't be a three-phase fault. Can't be a three-phase fault here. because they're not in series. I'm suspicious of this guy, right? I'm suspicious of this guy, but my voltages are not all the same. So I can be sort of suspicious of this phase to ground fault with this impedance, but I'm going to sort of eliminate it because my zero sequence quantity needs to be the same, right? Okay, so it's not this one. Can't be this one because I've got zero sequence current. As I look here, it could be this guy, it could be this guy, but in reality, it's going to be this guy. It's a phase to ground fault. The sequence networks are in parallel, so my voltages are the same. And it's this one because my zero sequence impedance is going to be a little bit different. So since it's a little bit different, that's why my negative or my zero sequence current is a different value than the positive. The negative sequence. Okay. When I print this out, I like to and give you handouts, which we didn't do today. I like for the answer to be hidden. So that's why that's there. Positive and negative sequence currents are equal and opposite. This is problem number 2. And there's no zero sequence current. Well, if there's no zero sequence current, what that immediately tells me is that either there isn't a ground source, or, but more likely, ground's not involved, right? So zero sequence is not involved. That means ground's not involved. So positive and negative sequence currents are equal and opposite. So I have to find a scenario where they're equal and opposite. Well, negative sequence isn't involved here, not involved here. Zero sequence is involved there, so that's out. That looks suspicious. Negative zero sequence is involved there, zero sequence is involved there. So does this meet my scenario? Let's see. Positive and negative sequence currents are equal and opposite. Zero sequence current is 0. Yep, it meets that because my currents are flowing in the opposite direction, right? So it's flowing that way here and this way here. So that means that that's got to be my culprit. Let's see if I'm right. Oh, I screwed up. It's actually this one down here, but that's the same sort of fault, right? The only difference is I didn't have. This one has an impedance involved in here, right? So yeah, I did miss that. The impedance would make my voltages on my positive and negative sequence. The fault impedance would make my voltages on my positive and negative sequence network a little bit different. So this is actually a solid 3-phase fault. There's no impedance involved. Okay. Okay, with that said, I said I would end right on time, and then I would need to take 15 to 30 minutes extra to address any questions that came up, and looks like I did pretty close to what I said I would do. So I'm actually 4 minutes over. So my apologies for the extra 4 minutes, but I think I got time for questions. Let's see. It looks like there's some chats here. Yeah, that beep was a pain in the neck. I have to agree with that one. Yeah. Okay. It looks like all the questions that are in the chat are around the beeps. So if you want to unmute yourself and ask a question, you probably can, or you can type a message into the chat, either one. And
that was great, Terry. Thank you very much.
Okay, I was just going to ask John if, since I wasn't hearing anything, I was just going to ask if, maybe I dropped off 50, the internet at my house dropped off 55 minutes ago.
No, you're still on.
Okay, good.
Yeah, I've done one of these too. It's like you're talking to yourself because there's very little feedback.
Yeah, that actually happened to me a long time ago.